Hello. On behalf of Alpha Omega team, today I would like to talk about mathematical background for calculating element quality. As you know, the elements or the mesh in our simulation, regardless if it is FEA or CFD, is supposed to represent our geometry. And if we don't have a good size of an element or a good quality of an element, then our results will not be trustworthy. So it is important to understand what are the categories of element quality and how we can measure those qualities to make sure we have good size of an element and good quality of an element. So with that being said, let's just review the mathematical background for calculating an element quality. Vectors. Now I'm going to give an introduction to vectors cross and dot production. The first set of equation is I cross j, j cross k, and k cross i, which all three can be calculated with right hand rule, and respectively it is going to be ki, and j. And j cross I, k cross j, and I cross k is going to be minus k, minus I, and minus j, respectively. And the production of I cross I, j cross j, and k cross k is going to be 0 because the angle between the two vectors is 0. Let's say we have two vectors, vector A and vector B, with the components A1, A2, A3, and B1, B2, and B3. Then the cross of these two vectors is going to be A cross B, can be calculated with this formula, or simply can be the determinant of the unit vectors and vector A and vector B. And this determinant can be calculated with this formula. Ignoring the first column, calculate the determinant of A2, A3, B2, and B3 and multiply it by I, minus ignoring the second column and calculating the determinant of A1, A3, B1, and B3 multiplied by j, plus ignoring the third column and calculating the determinant of A1, A2, B1, and B2 and multiplied by k. And the outcome of A cross B is a vector. Geometrically, what A cross B is representing is the area that vector A and vector B is making, which is basically a parallelogram. And the outcome or the production of this cross is going to be another vector perpendicular on these two vectors, and the magnitude of that vector is going to be the area that these two vectors is making. Now, if we want to calculate the magnitude of A cross B, is going to be magnitude of A multiplied by magnitude of B multiplied by sinus of the angle that these two vectors is making. Now, A dot B with n number of components from 1 to n can be calculated with this formula, which is the summation of AIBI, I from 1 to n. Let's say we have two vectors, vector A with the components of 1, 3, and minus 5, and vector B with the components of 4, minus 2, and minus 1. Then the A dot B production will be the first component of vector A multiplied by the first component of vector B, which is going to be 1 multiplied by 4 plus 3 multiplied by minus 2 plus minus 5 multiplied by minus 1. And the production of A dot B is just a number, is a scalar. It doesn't have any direction. And if we know the angle between A and B, then the A dot B can be calculated with the magnitude of A multiplied by magnitude of B multiplied by the cosine of the angle between A and B. And of course, if A and B are perpendicular with respect to each other, then A dot B is going to be 0. Now, if we have two vector A and vector B, and we are interested to calculate the angle between vector A and vector B, then that angle can be calculated from this equation, which the cosine of that angle is going to be equals to A dot B over magnitude of A multiplied by magnitude of B. Now, planes. In this section, I'm going to give an introduction to plane equation. There are three ways to form a plane in space: having three non-collinear points, one point and one line, and two lines that they have intersection. And of course, the line and point, they should be non-collinear. And mathematically, if we want to calculate and have the equation of a plane, if we have the normal of that plane and a point that is on that plane, we can also calculate the equation of that plane. So let's say we have 3 points in space: point 1, point 2, point 3, with the components of x1, y1, z1, x2, y2, z2, and x3, y3, z3. That, of course, they should be non-collinear. Then the plane equation that can have all these 3 points is going to be the determinant of x minus x1, y minus y1, and z minus z1. And the second row will be x2 minus x1, y2 minus y1, z2 minus z1. And the third row will be x3 minus x1, y3 minus y1, and z3 minus z1. The determinant of these metrics should be 0. If we have a point in space and we want to know what is the distance between that point and the plane, then we can use this formula to calculate that distance. That distance is going to be the magnitude of ax1 plus by1 plus cz1 plus d, which ax plus by plus cz plus d equals 0 is the plane equation, and x1, y1, and z1 is the point components. And if we divide that magnitude by square root of a squared plus b squared plus c squared, then this will give us that distance. The third equation is, if we are interested to know the angle between two planes, then the angle between two planes can be defined as the angle between their normals. And that normal can be calculated from the dot formula that we learned in previous section. N1 dot N2, which each of them is representing the normal for plane 1 and plane 2 over by the magnitude of N1 multiplied by the magnitude of N2. Thank you very much for paying attention to mathematical background for calculating element quality. In next video, I am going to use what we learned and reviewed today to calculate element quality, and I'm going to recommend certain limitations for each element quality to make sure we have a decent element quality so we can trust our results better. Make sure to subscribe to our YouTube channel for further training. Stay tuned. Thank you very much and have a good day.
Thanks for watching our video and hope you enjoyed it. Please make sure to subscribe to our YouTube channel for more videos.